session, part 2. The first paper is Open World Reasoning for Service Robots, and the speaker is Jiang. Please.
Okay. Good afternoon. I'm going to present our work on open world reasoning for service robots. I'm Jiang. This is joint work with Nick Walker, who is in the audience, and Justin Hart and Peter Stone. So imagine you have a very capable service robot at home. And it has all the vision capabilities and manipulation capabilities for the objects in your home. And you might want to give it a command like, get me an apple from the kitchen. Ideally, the robot just knows that where the apple is. And with current planning technologies, it's easy to generate a plan like go to bar, pick up. Hello. Okay. Is that good? Okay, so with the current planning technologies, it's easy to generate a plan like go to bar, pick up apple, go to user, and deliver apple. But the more likely scenario is that you ask, get me an apple from the kitchen. The robot has not seen an apple recently, even though it has all the vision capabilities for recognizing an apple. In this case, it's difficult to generate a plan. Because most classical planning technologies adopt a closed world assumption, which basically assumes that everything the robot needs to know is already in its knowledge base. However, the real world is open, just like this one, which means that anytime the next command the robot receives may refer to an object that is not currently in its knowledge base. However, the user might have some ideas about where an apple is, just like in this case, it's suggested in this command. And if it's not, the robot can easily do a dialogue with the user to ask for suggestions. Therefore, the aim of this work is to propose a unified system that reasons and plans in the open world to solve user-specified tasks. We plan to do this by leveraging the user's implied hypotheses of unseen objects. And then generic closed world planners can be applied to this task. In cases where the user's hypotheses are wrong, the robot will not be able to accomplish the task given those hypotheses. We also aim to provide diagnostic reasoning about invalid hypotheses and report back to the user. There's a lot of related work to this one, in particular in knowledge representation planning for service robots, just to name a few here. A lot of this research has been driven by the RoboCup at Home competition. In particular, there's a general purpose service robot test that features incomplete and erroneous commands. On the side of open world planning, several approaches have been proposed in this work. We focus on resolving the unseen objects by leveraging the user's hypotheses. To give an overview of our method, we plan to do this by closing the world by representing unseen objects referred to by the user as hypothetical objects. And then we can formulate any hypotheses that involve these objects that are implied by the user. And we use what we call realizer actions to explicitly model object search. This will allow feasible plans to be generated by closed world planners. And then, since we explicitly model these hypotheses, we can have diagnostic reasoning about these hypotheses using robust observations during plan execution. We start using a pretty standard formulation for the planning problem with the initial state, the goal condition, a set of rules modeling the actions and their preconditions and effects. But in this one, in an open world, information necessary for accomplishing the goal condition can be missing in the initial state. And we aim to generate a plan that's a sequence of actions to satisfy the goal condition. Each state for the robot is represented in its knowledge base as a set of concepts, a set of object instances, and a set of predicates describing the attributes and relations of these instances and concepts. For example, here you can see an water bottle instance that is an instance of the water bottle concept, which is a bottle, which is a container. And this water bottle instance in particular is placed on the dining table. Then we can proceed to closing the world by explicitly representing users' hypotheses. First, we extract from the user's command the goal condition, a set of unknown objects referenced by the user, and a set of hypotheses. Then we can create a new instance for each object that is unknown by adding two inheritance relations, one with its own object class and one with the hypothetical concept. Here, basically, this says this is an instance that is an apple, but also it's hypothetical. Then we add a hypothesis, each hypothesis to the knowledge base. In each hypothesis that uses these unknown objects, we use the hypothetical instances that we just created. For example, here this says this hypothetical instance ID can be in kitchen. But in the goal conditions that involve these unknown objects, we instead use their object classes. This is because we want to allow the planner to use the hypothetical instance at planning time to generate feasible plans. But after real instances of the same object class have been observed, the planner can switch to using these real instance IDs for the remaining plan. For example, here's a goal condition that says an instance of apple gets delivered to the user. Besides explicitly modeling the hypotheses, another pillar of this approach is what we call the realizer actions. They're just actions that correspond to physical perceptual behaviors that the robot can perform, such as the action scan surface. In the planning domain, their effects are to turn hypotheses into concrete attributes and relations. But this is only at planning time. In reality, at execution time, it will never actually produce observations of the hypothetical instance. Instead, the robot's vision pipeline will populate new observations into the knowledge base, such as there is a real object on the dining table and it's an instance of apple. The system has been fully implemented on real robot platforms. We implemented knowledge base using a SQL database. Planning and reasoning rules are encoded in answer set programming, and we use the ASP solver Klingo. We also have implemented plan executors to monitor and replan when necessary. Next, I will show a video demonstration of a robot successfully executing the command, "Get me an apple from the kitchen." Audio is... It says it's connected. Okay, there are captions you can see. So the robot is going to every surface in the kitchen, and the shelf heights for this cupboard are pre-populated in the knowledge base, so it knows to go up and check the upper shelf. Object manipulation was a little slow when we took this video, but we have improved since then. Okay, in cases where the user's hypotheses are wrong, since the hypotheses have been explicitly represented, we can do diagnostic reasoning on these hypotheses using the robot's observations. Specifically, we model a diagnostic rule that attempts to deduce the negation of any hypothesis based on the robot's knowledge. For example, we can say that a hypothetical object cannot be in the kitchen if all surfaces have been scanned and no such object is found. Specifically, we do this with an optimization query because we want to give the user the benefit of that to sort of maximize the number of hypotheses we can believe. Next, I will show a demonstration when the robot went to all surfaces, did not find the apple, and comes back and reports this. So it's now going to the last surface in the kitchen, which is a long table. And now no feasible plans can be found, so it's going to the operator. Okay, to summarize, we propose an approach for planning and reasoning in the open world for service robots. We do this by leveraging ontology to represent the user's hypotheses. And this, we also demonstrate the ability to handle a realistic request that requires the robot to plan with unknown objects and also do diagnostic reasoning to identify invalid hypotheses. For future directions, we like to explore other kinds of openness, such as map areas and unknown people, as well as other sources of hypotheses where we can leverage. For more details of this work, here are some links on the slide. And thank you for your attention. I'm happy to take any questions.
Hi, thank you. This is good work. I have two questions. One is in terms of the hypothesis objects that you're creating, how do you control for, there can be a lot of hypothesis objects, right? Is there some sort of, is there some sort of limit that you impose on them?
Technically, you can delete the hypothetical object you created for commands that you have accomplished. So it should be manageable. You just need to keep track of all the hypothetical objects for the current command.
Okay, so my second question is a follow-up to that, which is the diagnostic reasoning, which seems like a sort of closure condition to figure out if the object is there or not. How do you manually map those things to like the sensing actions? Because, so for example, if you're trying to look for the hypothetical object, presumably that's mapped to some lower level action or a sequence of lower level actions on the side of the robot where you do a scan of the room or whatever, right? Do you manually map that right now?
The planner generates scan surface actions for the hypothetical objects in this case. And after each scan surface, knowledge base will have the scanned property of the surface, and the diagnostic reasoning rule just produces something like, since all the surfaces in the kitchen have been scanned, then this object cannot be in the kitchen, which is direct contradiction with the user's
Right. So I guess my question is, how do you know the relation between the scanned surface action and the scanned predicate? You have to enter that, right, manually into the...
Yeah, that's like static in the planning domain.
Just as a follow-up to that last question, in fact, what I thought you were actually asking is, how do you know that the apple would just be sitting on a scanned surface? How do you know it's not in a drawer in the refrigerator or covered by something to keep it fresh? I mean, there's a million possibilities. That's why people have problems finding things, is because they don't look everywhere.
Right, so in this demonstration, we only said this apple can be on a surface, but in reality, you can be in kitchen, you can model that it can be anywhere in the kitchen. You can have a list of locations in the kitchen, including the fridge and the drawer. And if the robot is capable of opening the drawer, opening the fridge, it should be doable.
Other questions? Okay, so we can thank again the speaker. And the next presentation is Intruder Alert, Optimization Models for Solving the Mobile Robot Graph Clear Problem. And Margarita Castro will present, this is a journal paper.
Okay. Hi, everybody. Thank you for the introduction. I'm Margarita Castro, and this is a joint work with Professor Michael Morin in Laval University, and current and former students in our lab, Kyle Booth, Tony Tran, Chang Liu, and my supervisor, Chris Beck. And this work is called Intruder Alert, Optimization Models for Solving Mobile Robot Graph Clear Problems. So, the problem is basically we have a discrete environment, and we have some potential intruders on the environment, and we want to determine how many robots do we need to actually explore the environment and make sure that we find the intruders if there are any there. So there are many applications of these problems in mobile robotics problems, such as surveillance, search and rescue, and also building securities. So I'm going to explain the problem little by little. First, I'm going to explain what do we mean when we say clearing a room. So let's imagine that we have a floor like the one here, and we want to make sure that there's no intruder in room B. So the first thing that we need to do is to make sure that all the robots are blocking the entrances. So in this case, we assume that each robot can just see the cell that is on top of it. And then what we need is, so in this case, we need 5 robots, and also we need And we also, in this case, we need 4 robots to sweep the room and make sure that the intruder doesn't go around the robot or doesn't escape it. So this is how we clear a room. Now I'm going to explain how we can actually clear the whole floor and try to use as little number of robots as possible. So what we do is that we're going to transform this floor plan into an actual graph where the nodes are going to represent the different rooms and the edges are the connection between the rooms. And the numbers on top of the nodes are going to represent how many robots we actually need to swipe a room and to sweep a room. And the nodes, the numbers in the edges are going to represent how many robots we need to block an entrance. So for now on, I will assume that we have this graphical representation somebody formulated for us, and we're going to focus on how to solve the problem in this graph, okay? So as I say, now what we want is to find a sequence of nodes such that the graph is clear of all the intruders and we minimize the total number of robots that we need to clear the whole graph. So that's why it's called the graph clear problem. So the first assumption that we have is what we call the progressive assumption. So we're going to assume that once a room is clear, it can't get recontaminated. So we don't want to swipe a room 2 times. If it's clear, we're going to make sure that then the intruder can't move and go back to the room. So for that, what we need is first that when we sweep a room, we're going to block all the entrances. So for instance, here, if we want to sweep room A, we need to block the entrance here with 2 robots, here with 1 robot and 2 other robots just to sweep the room. And also when we then want to sweep the next room, we'll have to still make sure that there is a robot blocking the entrance, the edge between a clear node to a contaminated node, so it doesn't get recontaminated. And with this assumption, we only need to make sure that we clear a room only once. Okay, so I'm going to now show how a solution actually looks with this little example. So let's imagine that somebody tell me, hey, I want to clear the graph according to this sequence. So first room A, then D, B, C, and E. So the first room is easy. We just need 5 robots to clear it. It's just the sweeping and the blocking robots. But then in room D, we need to still make sure that we block this edge here. So we actually need 6 robots in total. Then if the next one is B, now we need more robots because we need 4 to swipe here, 3, 1, and 1 to block, plus 1 more here to make sure that we don't recontaminate the areas that were already cleared. Then we need 7 more robots if we clear room 6, room node C, and then 7 more to clear room 7. So now in this case, if we do a step by step, the maximum number of robots that we need is just the maximum over all the steps, so it's just 10. And this is the number that we want to minimize. So we want to try to find like a sequence of nodes such that the maximum number of robots that we need is as low as possible. So in this problem, in this work, we have 3 main contributions. First, we present new theoretical results on this, the progressive assumption and other assumptions about the problem. We also show the first model-based approaches to tackle this problem. Before they were just heuristics. And also we analyze and study a little bit the heuristics that were there in the literature, and we propose some improvements. So in the theoretical aspect, well, the first thing that we were wondering about this progressive assumption, like, does it actually make sense to don't allow recontamination? Can we actually get like a better solution if we allow to recontaminate and then clear a room again? And the answer is, we're not sure yet. But we make a little bit of progress, and we found some specific type of recontaminations that didn't help us. So we think that clearing a room and then contaminate it again doesn't work, but we're still not sure, and there's room for new research, at least in this area. And the other assumption that we were wondering it was the contiguity assumption. So especially if you have a floor room, the most intuitive thing to do is like clear a room and then clear the one next to it, and then clear another room that is next to something that is already clear. So that's what the contiguous assumption means. And for a long time, we were sure that this would keep optimality, and then we were surprised that it actually didn't. And we found this example graph that it shows the optimal solution is not contiguous, and if we impose the contiguity assumption, we get suboptimal solutions. And I like to call this the death star, because it looked like a star, and it killed all our hypotheses. So in terms of model-based approaches, we present a mixed integer programming model and two different CP models. The first one is called the node-based model, and the second one, the sequential-based one. So I'm going to now very quickly present the models, and I'm going to bore you with all the details. But basically, in the MIP model, what we have is two different binary variables that represent if I clear a certain node and a certain step. And we just have then a bunch of constraints, making sure that we block all the edges when we swipe a room, we don't allow recontamination, and we can compute the cost in each step. Okay? So then the node-based CP model, this one has much more variables. We have some variables for that tell us which is the step that we sweep a node. And also we have 3 variables to represent the blocking of an edge. We have some like when is the first time we block an edge, when we release it, and if at a specific time the edge was blocked. And also a couple more variables to represent the possible cost in each step. And then of course all the constraints to make sure that everything is consistent. And lastly, and this is the beauty of using CP, you can have a huge model, and then like you think a little bit more, and you can have like a very little model with very few constraints. So here we just have one variable that is the node sweep at time step t. And then we have just, as you see, like 3 lines of constraints that represent the cost of in each step, and making sure that we clear all the nodes. Okay, so I'm not going to go to the details of this, but that's why we like these techniques, because you can think it through and make like really nice models. So in the heuristic approach, what people were doing in the literature, I'm going to explain the heuristic, is that you take your graph, you take some of the edges to get a spanning tree, and then they compute a solution for that spanning tree. They're still not optimal for the tree, because the problem is still hard in that case. But you get a good approximation. And then they use the solution for the tree to compute a solution for the whole graph. So the question, and that's the part that we were curious about, is like, how do you construct this spanning tree? So what they were doing in the literature is they were using the minimum spanning tree. So they were removing all the edges that were very costly and just keeping the ones that were very cheap. But the problem is, and that's what we were thinking, well, if you remove all the edges that are very costly, you're going to get a very weak relaxation. The cost of the tree is going to be very far from the cost of the graph. So you say, well, maybe we can just try the opposite. What happens if we just use the maximum spanning tree? So we keep all the most expensive edges, and we are hoping that if we do that, the cost of the tree will be similar to the cost of the graph. So in terms of results, we compare with different types of graphs, random graphs and also planar graphs that is more similar to like the floor in a building. We have with 20, 30, and 40 nodes and different densities, very sparse or very dense graphs. We use CP optimizer to solve the CP models, and Cplex to solve the MIP models. And the experiments, we have 2 sets of experiments. First set, we were interested in like, can we actually find the optimal solution? So we have a 1 hour limit, and we use our model-based approaches for this. And the other part was the feasibility. well, maybe you don't want the optimal solution, but you want a solution fast. So we have a 30-second limit. We compare our heuristics with the best solution that our models gave us in 30 seconds. So here are the results for the optimality. So we can see here we have the different type of graphs, number of nodes, number of instances. So we have like, for planar graph with 20 nodes, we generate 20 random graphs. And here we have the number of instances that we solve to optimality. And you can see that the problem is really, really hard. Like the MIM model is the one that solves more instances, but it only solves for very small problems. And it just solves in total 32 of the 135. And the CP does very poorly in this case. But the interesting thing here is that when we compare the solution quality of our models, it was the complete opposite. CP was finding much better solutions than the MIP models, even though it wasn't proving optimality. And so depending on what you want, it might be which type of models you want to use. So in terms of solution quality, we compare the two heuristics, minimum spanning tree and maximum spanning tree. And here what we have is a planar graph, random graphs, and all the points above the diagonal means that our maximum spanning tree heuristic was performing better than the minimum spanning tree. So it was more or less what we expected, but it was really nice to actually see it in the results. And the other interesting graphs here is when we compare the heuristic with the model-based approaches. So this one is going to take me a little bit more time to explain. Okay. So here, well, I'm going to explain for one graph. They both mean the same. So here, this line here is in one is the solution found by the heuristic. And we have the lapsing time, so we can see the evolution of each of the approaches over time. So these two lines here are the CP models. Here is the MIP model. So the MIP model, it didn't improve at all the solution in the 30-second limit. But for the CP models, we can see that over time, it improves the solution, and it took 30 minutes to actually start getting better solutions than the heuristic. And we see the same here when we have random graphs. So yes, so now I'm going to just conclude my presentation. We presented 3 model-based approaches to tackle this, the graph clear problem. We also present new theoretical results, and so we have a better understanding of what's the problem and what are the difficulties. And our experiments show that, well, using maximum spanning tree, it makes much more sense than using minimum spanning tree. CP is very, very good at finding high-quality solutions. So if you want something that finds you a feasible solution for these problems or variations of it, you should probably explore using constraint programming. And if you want optimality, mixed integer programming is still the best way to go. So thank you very much. And this, since it was part of the journal track, you can find our paper here in the constraints journal. Yeah, so thank you.
Hi, thanks for the talk. To be honest, I was confused with the example at the beginning because it had some hidden assumptions about what robots can and cannot do, I guess, and also the time horizon. Because, for example, you can imagine that there will be one robot that will sweep the whole floor, the whole room, while the others kind of keep guard. So I assume there are some constraints that prohibit the robot of doing that.
Yeah. So, yeah, let me go back to the example maybe. Yes, so there's a lot of literature about like how to actually model this part. Our work, it wasn't necessarily on this part, but well, so the problem is assuming that we have 4 robots because of that. Like you want them to start like exactly at the same time so nobody can pass between them. So it's like a wall like sweeping the whole room. But there in the literature a lot of like more assumptions and different ways that you can sweep the room depending on the robot. It might be that it actually can look everywhere. We're assuming that the robot is just looking front. But depending on the assumptions of how your robots are, the problem might change a little bit. So that's why then we just abstracted to a graph. So, and we study just the combinatorial part.
Okay, and one more question. If the robots have different capabilities, for example, in terms of battery life or in terms of, so let's just think about battery life, and maybe when a robot stands in the entrance to the room, they consume less energy than if they're actually doing the sweeping and so on. Mm-hmm. To what extent will that really make the model far more complex?
Yeah, I think in that case, it will definitely, you have to consider the consumption, because as you said, like it makes sense that maybe in that case, instead of like clearing one room at a time, you will want to clear multiple rooms at a time to make sure that you satisfy your energy consumption. So yeah, you will, I don't have in the tip of my mind like how to do it, but you will have to for sure introduce more variables and more constraints to model those kind of situations.
So as a follow-up, the assumption here that the robot can only see in its current cell seems different than most types of person detection systems. But presumably, relaxing that assumption or changing it maybe just changes the structure of the graphs. So I wonder, have you thought of sources of a more representative distribution of graphs as opposed to random or just random planar?
No, we didn't study any more like specific graphs. We were really wanted to like find like actual building and try to implement it there, but they were usually very small, so it was very, very easy to solve. And also we wanted to use like this specific type of robot that are very myopic. Of course, if you use, for instance, drones, you can do much more interesting things and like maybe have like an area distribution of how the visibility of the robot. But we just wanted, since it was the first step to how to use these model-based approaches, we try to keep it as simple as possible.
I was just wondering, are there any other graph properties that you think might be helpful as a heuristic rather than in addition to the maximum spanning tree that you thought maybe could be informative?
Yeah, so we are not sure. We actually tried to study a lot if there were some nice properties. We thought that maybe solving the problem over trees would be easy, but no, still the problem is quite hard, it's NP hard. The general case is NP hard, and even when you reduce to trees, it's NP hard. We noticed that when it's like, if we have a line, then it's easy. Then you can solve it right away using a heuristic, but we haven't found more graphical structures that can do that.
So just because a lot of the questions are about the assumptions and about the problem definition, so we didn't invent this problem. We've taken this problem and all these assumptions that we're using directly from the literature, and our contribution was thinking that, well, maybe these model-based techniques can actually do a much better job of solving these problems than the heuristics that were in the literature. So all these questions are actually really good questions about people doing robotics, but we weren't doing robotics in this case. We were taking a robotics problem that had appeared in the robotics literature and using their definition to see if our technology could solve it.
Other question? We can thank the speaker again. And the next talk is about probable infinite horizon real-time planning for repetitive tasks, and Fahad Islam will present. Hello.
Okay. I'm Fahad, and today I'm presenting Provable Indefinite Horizon Real-Time Planning for Repetitive Tasks. This is joint work with Oren, Salzman, and Max Likhachev, my advisor from Carnegie Mellon University. So we are motivated by motion planning problems in warehouse settings where the tasks typically are very repetitive, yet performance critical, so we need fast planning times. I'll show you a few examples of such domains. So here, this robot is working on a conveyor belt where the objects are coming in at a fairly high speed, and the task here is to pick up these objects and then put them in different bins. Now, the robot has a fixed time budget to plan within. If it fails to plan within that time budget, then did the video play or no? Okay. So if it fails to plan within that time, then it will miss objects, and we don't want that to happen. So we want robust and efficient motion planning. So here is a second example. It's an industrial robot working in a warehouse setting where the robot has to perform a sorting tasks. So it is picking up objects and then sorting them in these cubby shelves that you saw. So again, to have a good efficiency in such warehouse, it's critical, and we want fast planning times. Finally, in this last example, this is a project that we are doing in collaboration with Honeywell and NREC at CMU. It's a truck unloading robot that you see. The task here is to unload boxes from these delivery containers. And we want to increase the throughput of the system. So we want to increase the rate at which the robot is unloading boxes. So again, we don't want extra delays or overheads because of lazy motion planning. So in all these domains, we observe that motion planning needs to be fast and often provably bounded in time. We also observe that the environment is fairly structured, and the models, like the environment is known. So we won't see any objects online that we don't have a model of. And finally, we observe that the tasks are very repetitive. So the question that we are asking ourselves is, can we provide provably bounded planning times by leveraging pre-processing, given the environments that we are dealing with are known? And to the best of our knowledge, none of the existing algorithms provide such guarantees on planning time. So to formulate our problem, we make the following assumptions about the domain. We assume that the environment is known, as I explained, so the robot will not see any object online that it doesn't have a model of. We assume that we have a set of start configurations. So for example, again, in this conveyor example, the start configuration can correspond to the drop-off positions where the robot is dropping off objects. Again, in this truck unloading domain, the drop-off position, the start configuration is the configuration of the robot where it unloads the boxes. And corresponding to each start configuration, we have goal regions. The reason we need goal regions is we want to allow perturbations in the goal poses. For example, again, in this conveyor domain, the object that is coming in can be a different x, y position and orientation, and we want to be able to handle that. So now we have an idea of what kind of setting we are dealing with. Here is a 2D example of the same setting. We have a start state. We have a goal region, which is shown as this dashed region, and we have some obstacles which are shown in red. So the first thing that we do is we discretize the goal region so that we have finite number of states in the goal region. Now, one could think of that, why can't we just enumerate all the states in the goal region and pre-compute paths from the start state to each of those? The problem is that in this 2D example, it's possible. For higher dimensions, we will very quickly run out of memory. Also, if you have like 1 million states in the goal region, it'll take forever to pre-compute these plans. So can we do something better? So the key insight of this work is that given a potential or a heuristic function in some attractor state, typically there is a large region around that state within which the states can reach the attractor state following that potential or heuristic function. We call these states as reachable states, which are marked as these white states in the region. So instead of having to pre-compute paths to all the states within this region, we only need to pre-compute a path to the attractor state, and then at the query time, we'll use the potential function to find a path from any goal state that may lie in this region to the attractor state. And then we'll combine the two paths, pi I, and the path given by the potential function to get the final path from start to the go. Now, another point is that you can think of this method as a compression mechanism. So instead of having to pre-compute paths to all the states in the goal region, we want to compute a minimal set of paths which can still cover the goal region. And the quality of this compression depends on the quality of the heuristic function that we're using here. The better, the more informed the heuristic function is, the larger the regions we'll get, and the lesser the number of paths we'll have to pre-compute. Now, once we construct one such region, we have to construct multiple similar regions, ensuring that no state in the goal region is left free. So every state is covered by at least one subregion. So more formally, we decompose G into a set of subregions R1 to K, each defined by an attractor state in a radius, such that the union of all these regions R1 to K completely covers G. Now, this was the pre-processing phase. Now, what will happen in the query phase? Now, once we have these regions that we have pre-processed, we get a query, which is a goal state. The first thing we do is we identify which subregion this goal state belongs to using the radii of these regions. And then we simply follow the potential function, which will lead us to the attractor state. And the way we construct these subregions ensures that we don't have to do any collision checking in this step, which is typically the most expensive step in motion planning. And then we just combine this path pi g with the pre-computed path pi I to get the final path from the start to the goal. So this was the overview. Now let's look into some of the related work in this domain. So our algorithm at a high level falls in the class of pre-processing based motion planners. The most renowned among them in the motion planning community are probabilistic roadmaps from 90s. So PRMs construct a roadmap in the continuous space by randomly sampling states in the free space and trying to connect them. And at the query time, they try to connect the start and the goal state to this roadmap and use any graph search algorithm to find a path from the start to the goal. But these class of planners they provide asymptotic guarantees, and we are looking into more deterministic guarantees. Subgoal graphs also construct a roadmap, but in a grid world, in a discretized space. Similar to our method, it identifies a set of attractor states and then construct a roadmap or a subgoal graph from those attractor states, maintaining the property that every two states which are connected by an edge on this sparse subgoal graph are reachable. So they can use this subgoal graph online to improve the planning efficiency. But for two reasons, this algorithm is not applicable to our setting. One is that they require pre-processing the entire state space, which is not possible for memory limitations for higher dimensions. So it's only applicable to 2D or at maximum 3D domains. Second is that at the query time, they require running a Dijkstra-like search to connect the start and the goal state to this subgoal graph, due to which we cannot provide bounds on the planning time. Similar ideas were also explored in the controls community. These listed papers, they distribute the configuration space into control-specific regions, and online they use region-specific policies for robust and safe execution in these local regions of the configuration space. And these were the papers that inspired us for this work. Finally, in the context of bounded time planning, there is a family of planners called real-time planners. They provide bounds on the planning time, but they only plan for a finite horizon, giving partial paths, and then they typically interleave planning and execution. So we see that none of these algorithms provide bounds on the planning time for problems which are of indefinite horizon. Now let's look into some of the details of the pre-processing step. Again, we have a start, we have a goal region, and some obstacles. The first thing we do is we arbitrarily pick an attractor state from the goal region, and then we pre-compute a path from the start state to the attractor state. And this can be done using any off-the-shelf motion planner. It doesn't have to necessarily be a search-based planner. Then we have to construct the subregion for this attractor state. Now recall that we define reachable states as the states which can reach the attractor state following the potential function. So it turns out we can compute this region very efficiently using a single Dijkstra-like search by using a recursive rule that I'll explain in a bit. So what we do is we run a search from the attractor state and expand states in the order of not the G values, but the heuristic values. And the heuristic here is the Euclidean distance to the attractor state. I'll show you a little animation of this search. Now let's analyze what happens in a single iteration of this search. So assume that we have already marked these white states as reachable. Now for a newly expanded state, we see if the best predecessor of this state, according to the heuristic function and some tie-breaking criterion, is reachable or not. If that predecessor state is reachable, then we label this state also as reachable. And we use this recursive rule in this search to label all the states which are reachable for this attractor state. Now the search continues, and it then terminates when we find the first state which is unreachable. So the unreachable state obviously is the state which cannot reach the attractor function following the heuristic. More specifically, for this state, the best predecessor according to the heuristic function leads to a collision. So we stop here, and the heuristic value of this state gives us the radius of this subregion. Now, because we expand states in the order of the minimum heuristic values, we guarantee that all the states which have heuristic value less than the heuristic value of the last expanded states are contained in this region, and they are reachable, which are shown as these white states. Now, after the first region is constructed, we sample another attractor state in the region in anywhere in G in the area which is yet to be covered. And the process goes on and on until we get full coverage of the goal region. Now let's look into some of the theoretical properties that we provide. Our approach is resolution complete in G, meaning that with respect to certain resolution that we come up with, for any goal state that lies in G, if a path exists from the start state, the algorithm will guarantee that it provides that path. We show a query time complexity of order of the number of regions that we pre-process plus the product of the depth of the largest subregion and the branching factor. So the depth of the subregion here is, it corresponds to the number of states that you will have to expand at query time if the goal state happens to lie on the boundary of the largest subregion. So it's the worst case. So you can analyze this complexity easily. So at query time, given the query state we have, in the worst case, we'll have to do a search over all the regions to identify which subregion the state belongs to. And then in the worst case, we'll have to perform D expansions with B as a branching factor. And that's our complexity. That's all. We also provide a suboptimality bound, assuming that the planner that we use for pre-computing these paths, Pi, is optimal. We provide this additive suboptimality bound. So the difference between the cost of the optimal plan and the plan that our planner generates is no more than 2 times the cost of this path pi g that the potential function gives us at the query time. We evaluated our approach on 7 degrees of freedom motion planning problem for this PR2 robot. So the task here is that the robot has to pick up mail from the cart. So it's a mail sorting task, and then place them in these cubby shelves. So we define the goal region in this problem in the task space of the robot. So the goal can be any arbitrary position and orientation within these cubby shelves. For the experiments, we randomly sample states. We randomly sample poses in these cubby shells to get our results. We compared our approach against probabilistic roadmaps and MQRRT. MQRRT is a multi-query variant of RRT which we came up with. So in the pre-processing step, we generate a very dense RRT tree rooted at the start state. And at the query time, given the goal state, we try to connect the goal state to k nearest states in the RRT tree. And if it fails to find a connection, then it's a failure. For PRM, again, we also construct a dense roadmap offline. And we add the goal state, the PRM in the pre-processing step, the start state. And at the query time, we just try connecting the goal state to the PRM. And if the connection fails, or if the start and the goal belong to different connected components of the PRM, then it's a failure. We also compared with experience graphs, which is a search-based planning algorithm that uses experience to improve planning efficiency, and RT Connect. We observed that our algorithm takes about 24 minutes to pre-process the goal region in this domain. And we allow PRM and MQRT, which are the two other pre-processing based algorithms, to use 4x the time that we give our method, so about 2 hours. And we observed that none of the other 4 methods reach a success rate of more than 90%. Also, we show an improvement of planning times of over an order of magnitude over PRM and MQRT, which are the fastest amongst the other planners. In terms of memory usage, for this domain, our method only consumes 7.8 megabytes to pre-process this region. On the other hand, you can see that the PRM consumes about 2 GBs of memory. Now, to the bottom left, this is the plot that shows the pre-processing time versus the memory usage. And as you would expect, as the pre-processing time grows, the memory requirement of PRM and MQRT increases, whereas the memory requirement of our method is shown as this cross here. To the bottom right is the plot that shows pre-processing time versus the success rate. And as the pre-processing time increases, the success rate of these algorithms increase. But if you notice, for instance, for PRM, it starts to plateau over here. The reason is that typically sampling-based planners suffer from narrow passages in the configuration space. And of course, we have a success rate of 100%. In conclusion, we proposed a pre-processing-based method to provide provably bounded planning times for a given environment. And we evaluated our approach on 7-DOF motion planning problem. In the future work, we want to extend this approach for environments which are not completely static, but we want to allow some perturbations. We can explore how we can intelligently sample these attractor states to get better compression. We can also look into how we can utilize multiple heuristics instead of having a single heuristic function. And if possibly, we can provide bounds on the memory requirements. So with that, I'll conclude, and I'll be happy to take any questions.
Thank you for the nice talk. I didn't get the connection between the very exciting motivating examples and the actual method, because the motivating examples also seemed time variant, but your formalization here is just configuration space and not configuration cross time. And the other question I have is, you're trying dense roadmaps. Why not try sparse roadmaps? There's a lot of tools in that area as well, so as not to have the issues with the density.
Right. So referring to the first question, if you're referring to the conveyor domain, where the objects are coming, so it's a dynamic environment. So if currently we are looking into exactly the same problem, how we can solve that using our approach. So if you think about it, if we include time as a dimension for planning, the environment becomes static. So if you know the object that is coming in.
But can you still pre-process the goal and know the goal perfectly? Even in the example that you showed in your results, once you put the mail inside there, you have new obstacles as well inside the goal region. So how can you trust the pre-processing that you have done without the new obstacles?
In the mailroom scenario? So the video that I showed you in the beginning, you have scenarios where the objects that you put, they just flow through they are on inclined surfaces, so they just go away when you put them. Also, the example that we give is in a mailroom environment. So typically, the mails don't collide with one another. It's picking up an envelope, and then it's placing them in these cubby shelves. So if you place the first envelope, the second one will not collide with the first one, right?
So you have to have this property,
right?
In terms of
the
density on the roadmaps question.
Right. Yeah, so you're talking about sparse 2 and sparse from OMP. Yeah, I mean, we didn't experiment with that, but definitely you can reduce the memory requirement by using those instead of using PRMs. So one way we could compress also the requirement of memory from PRM is that we can, like we did that here. So we pre-configured paths from every state in the roadmap to the start state. So we don't have to construct the whole, we don't have to store the whole roadmap. We only need paths, right? Because the start state is fixed. So that we did here. But yeah, definitely you can reduce the memory requirements, but still it's you cannot provide completeness guarantees. Right, yeah.
Okay, if there are not other questions, we can thank again the speaker and switch to the next one. Okay. So the next paper is a short paper. The title is Speeding Up Search-Based Motion Planning via Conservative Heuristics. And the speaker is Ishani Chatterjee.
Am I audible? Okay. Hello, everyone. Today I'll be speaking about speeding up search-based motion planning via conservative heuristics. This is joint work with Professor Maxim Likhachev, Ashwin Khadke, and Professor Manuela Veloso. Okay, so we are looking at high-dimensional motion planning problems, such as planning for humanoids. Here you can see the Now robot and the Warwick. This has 34 degrees of freedom. So they often need to find paths in cluttered environments. For the purposes of illustration in the next few slides, I will use this simple example of planning for the position and orientation of this robot base, which is given by x, y, theta. So the starting position and orientation forms one robot state shown by the red point. If the robot changes its orientation, this becomes another point. Similarly, all possible positions and orientations represent the state space for this planning problem. One move by the robot corresponds to one edge between two states in the state space. So now we want to find a path from the start to goal in this state space. So weighted A-star search is a popular technique for search-based motion planning to solve this problem. It uses an estimate of cost to goal, which is the heuristic. Heuristics are often computed in an abstract space, which is a lower dimensional space. So in our example, if I drop the theta from the state space, so I get this 2D XY space consisting only of the 2D positions of the robot. So one 2D position forms one state in the abstract space shown in blue. Multiple states in the state space having same position but different orientation project to one unique state in the abstract space. The abstract space can have its own edges, so all possible projections will give me the abstract space. Okay, so a commonly used admissible heuristic is the cost of the shortest path to goal in the abstract space. So in our example, if I find the minimum area of the robot, which is shown by the in circle in red, the cost of the shortest path for this in circle is an admissible heuristic. So we see that the in circle actually passes through this narrow passage, and therefore the shortest path to goal for this in circle is this path shown in blue. So the search using this admissible heuristic expands only to find later that this is an infeasible path because there is not enough room for the robot to turn. So the search eventually does find a feasible path to goal, but only after expanding many such infeasible paths and thereby wasting search efforts. So then the question is, can we come up with a heuristic function that right from the beginning guides the search along a feasible path? For example, in this case through this green path that passes through the wider space where no matter what the orientation of the robot is, it can always make a feasible transition. So a search using such heuristics will always, if it expands along this path, because it's always feasible, so it reaches the goal. So I want to make it clear that we are not coming up with a novel abstract space, but given an abstract space, I want to compute heuristics to reduce search expansions at the expense of cost optimality. Okay, to compute such heuristics, we define conservative edges in the abstract space. What's a conservative edge? An edge between two states in the abstract space AB is conservative if for every state in the original space that projects to A, there is at least one valid edge to one of the states in the original space that projects to B. So in this example, if one of the edges in the state space was missing, then AB would become a non-conservative edge. So why care about conservative edges? So imagine in the abstract space, if we could have a path from start to goal that is consisting only of conservative edges, then that means we have actually found a solution in the state space. So let me tell you that computation of conservative edges is domain dependent. However, it is this very domain knowledge that helps us to compute conservative edges efficiently, as we will see in the case of our running example. So if I take the robot and I find the maximum area that the robot can occupy independent of its orientation, which is given by the circumcircle. So I take the obstacles and I inflate the obstacles by the radius of the circumcircle. So any edge that lies outside this region is conservative. Why? Let's take a closer look. Consider this edge AB that is partially inside this inflation region. For some orientations at A, the robot can make a feasible transition to B, and therefore that edge in the state space exists. However, for other orientations at A, the robot cannot make a feasible transition because it leads to a collision, and therefore this edge does not exist in the state space, and AB becomes non-conservative. However, consider another edge CD that is completely outside this inflation region. So no matter what the orientation of the robot is at C, it can always make a feasible transition to D. Thus, all of these edges exist in the state space, and AB becomes conservative. So people have looked at using abstract spaces to improve search efficiencies rather than to compute heuristics, such as hierarchical planning methods. So they find a plan in the abstract space and refine it to a full dimensional plan. However, our work is more closely related to the body of work that uses abstract spaces to compute heuristics. However, most of the work focuses on computing admissible heuristics to find optimal plans. In our case, we are willing to trade off cost optimality to get speed up of search. The strong matching property and the weak refinement property come close to the conservative property. Except for that, it's not a requirement in our abstract space. Our abstract space can very well have edges that do not satisfy this conservative property. Moreover, none of the existing works, to the best of our knowledge, compute heuristics by explicitly minimizing the number of non-conservative edges. And also, mostly work is focused on classical planning domains, whereas our focus is on motion planning. Okay, so we have the notion of conservative and non-conservative edges in the abstract space. So the heuristics should guide the search along paths that minimize the number of non-conservative edges. In order to do this, we run a single backward Dijkstra search from the goal to all states in the abstract space, but we modify the edge costs. Okay, let's take a look at the modification. So we modify edge costs according to this scheme, where Cmin is the minimum cost of an edge in the abstract space, NCO is the total number of conservative edges, and alpha is a factor greater than 1. So this guarantees that in the abstract space, for any purely conservative path, its cost is guaranteed to be less than any path that is not purely conservative. So what this means is that if a purely conservative projection exists in the abstract space, the heuristics will definitely guide the search along that path. So it's a known fact that for weighted A star with weight W using consistent heuristics, the cost of the solution found is less than or equal to W times the cost of the optimal path. But using conservative heuristics because of the alpha factor, because of the cost scheme, an additional factor of alpha is introduced in the cost suboptimality bound. Also, we show that for a purely conservative path, if it exists from the abstract start to goal, then for a sufficiently large weight on the heuristic, the number of expansions by weighted A star is exactly equal to the number of edges in the shortest purely conservative path. So we evaluated our approach on path planning for UAVs with the XYZ as the state space and the XY as the abstract space. So we see that there is a reduction in the planning times by almost a factor of 10. So the baseline heuristic here is just computing the optimal path in the abstract space without the notion of conservative edges, while we see that the mean solution cost and the heuristic computation times have remained almost similar. We also evaluated our approach on the humanoid footstep planning domain. So here the robot has to plan with an initial set of obstacles, and as it starts planning, new obstacles are added on its way, so creating this narrow passage, and therefore fast replanning becomes extremely useful in such cases. So we see that weighted A* search using our conservative heuristics is quickly able to replan a path around these obstacles and reach the goal, whereas the baseline is struggling to find a path. Okay, so we define the notion of conservative edges in the abstract space. We proposed a heuristic computation algorithm that minimizes the number of non-conservative edges, maintains some theoretical guarantees, reduces state expansions by weighted A*, and we applied it to several motion planning domains and obtained reductions in expansions and planning times. Thank you. I'm happy to take questions.
So there is this work on multi-heuristic A*, where you can use multiple heuristics and guide it, I think also from Max Likhachev's group. Do you see here some interaction potentially these conservative heuristics together with?
Yeah, so the multi-heuristic A*, if I'm not mistaken, will need one admissible heuristic and others can be inadmissible. So I guess conservative heuristics can serve as one of the additional inadmissible heuristics that can take it out of a minima region if one of the heuristics takes it to a minima region.
But you haven't tried yet to see
no,
in terms of
no,
okay.
But that's a nice suggestion. I'll take into account.
Questions?
So I'm just curious, do you have any requirement for what does the age means in the physical world? So basically you have a conservative age, which is in the abstract space, right?
Sure.
So that actually corresponds to the age in the state space.
Yeah, so
right?
Yeah.
So I'm trying to figure out that it seems to me, depending on the type of robot you have and depending on the type of local planner that corresponds to the ages in the state space, would your claim that what the theory actually holds?
The claim about?
So if you have a robot manipulator, for instance,
yeah.
then your ages actually might actually correspond to a non-straight age motion in the state space, right?
Yeah. So the straight lines were shown for illustration purposes. Actually, it is any valid connection from a given state to the successor. So it doesn't really have to be a straight line edge as long as there is a connection with it's about a state and its successor, and it should be able to have a valid transition to the successor. And it depends on the state space. Like for like in my example, for the xy theta, from one xy theta, it should be able to go to another xy theta. Now it can be a straight line, it can be a curve.
Yeah, I understand that, but I guess what I'm trying to get at is that is it always if I have different local planners, so that each ages, different ages that corresponds to a particular conservative age actually corresponds to different behavior of motion. Does this also hold? So you just apply it to using different local planners?
Yeah, for a given planner, you need to take a look at.
So you have multiple local planners that are applied for a particular conservative age?
No. So to find conservative edges, I don't really need to go back to the state space to check if it's valid. Like I can use domain knowledge to find. And this is just one planner, one weighted A* running in the state space, and one planner that has already been run in the abstract space and given me the heuristic values. So currently it's for one planner, and the successor generation. So the edges will depend on the successor generation function.
Okay, perhaps let's try. Let me ask later.
Oh, sure.
Let's thank the speaker again. And we will switch to the next speaker. This is a long presentation a hierarchical approach to active semantic mapping using probabilistic logic and information reward POMDP. And the speaker is Tiago Veiga.
Okay. So thank you. Yeah, so I'm Tiago. I'm presenting this paper entitled Hierarchical Approach to Active Semantic Mapping Using Probabilistic Logic and Information Reward POMDPs. Work done within an internal collaboration in our research group. During this talk, I will start by briefly motivating for our problem, describe the architecture that we propose, its execution, present some experiments, and conclude. Our main motivation for this problem comes from our experience, our group experience at the RoboCup at Home and the European Robotics League competitions, where domestic service robots must maintain and improve their perception of the environment. And from these, two research questions led our work: how to create and update a semantic knowledge representation of dynamic environments, and how to make decisions that improve the information and use it to carry some tasks. Our approach, our approach is a combination of a hierarchical combination of probabilistic logic and decision theoretic planning that takes advantage of the benefits of both. So in the case of probabilistic logic, it's an efficient representation of probabilistic knowledge. In the case of decision theoretic planning, its capability of making decisions with the incomplete information. But at the same time, mitigating the disadvantages of both. So probabilistic logic lacks decision capabilities, while decision theoretic planning lacks scalability. Before going into detail, just a few definitions. So we define a global state space that is composed by a set of state variables that represent features of interest in their environment. Each state variable has a particular domain. Then we divide the environment into regions, and each region has a local state space that is composed by a subset of the global state variables. Each local state variable has a domain that is also a subset of the domain of the global variable, plus one value, none, that is used to indicate the possibility that a given feature is not present at that region. And then we define a function f that translates the domain of global variables to local domains. And so our architecture, our proposed architecture, globally looks like this. We have two layers: the knowledge representation layer that uses probabilistic logic, is implemented in the Problog language, that represents the global knowledge of the system. Represents the global state space and keeps a belief of the global knowledge of the environment. And it's built from a world model that is inputted to the system. It also implements a reasoning engine that updates the global belief given the observations that come from the execution layer, that in turn is composed by a set of POMDP models, one for each of the regions of the environment. These POMDP models are modeled within the POMDP with information reward framework that compute policies to optimize the information gain. Okay, sorry. Here, just to mention that there are two levels of decisions. So there's a macro decision level that happens in the upper layer that decides which region should the robot to explore which region should the robot explore, and then inside its region, each POMDP model drives the interaction between the robot and the environment. And so the question comes, how to select which region to explore, so basically how to select which POMDP model to follow. We take into account two criteria in the paper. So if the global objective of the system is to carry a physical task, so for instance, to grab an object, which location we don't know a priori, then we choose the POMDP, which has the policy that induces the highest value for the current belief. This is similar to what is done in the auction POMDP framework that has also been proposed in the literature. On the other hand, if the goal is purely an information gain goal, for instance, if we are building the semantic map of the environment, then we do the opposite. We choose the POMDP model whose policy returns the lowest value. The reason behind this is that we're using the POMDP with information rewards framework. That so it's optimizing to information gain, is rewarding for information gain. And the property that POMDP's value functions are piecewise linear convex. When the POMDP is executed, the policy will drive the belief to corners of the simplex. And so if we choose the value with the minimum, we choose the POMDP model with the minimal value, there's a higher potential for an increase in the knowledge or to reduce the uncertainty of the system globally. Okay, so after choosing one model, it executes its policy within the local region. The POMDP model keeps and updates its internal belief, but at the same time, it outputs the observations that it receives in that local region. These observations are then outputted to the knowledge representation layer, to the upper layer, which after the execution of the POMDP, that executes until some stopping criteria, then the upper layer smooths the global belief with an exponential decay and computes the posterior probability given the observations that come from the POMDP execution, and therefore updates the global belief of the environment. Okay, I will present some experiments that we made. First, show our setup. So we tested this in a simulated apartment that we have in our lab. This is the image of the apartment and the map. So we divide each division of the apartment is a region in the sense that I was explaining before. Inside each division, there are some places that are considered. And in our case, we want to export the environment to detect actually consider three mobile objects that can be located in any place. So we have a box of Pringles, we have a Coke, and we have a mug. And the model for this environment includes two kinds of state variables. One for the position of the robot, one for the position of each object, one observation variable per each object that tells whether the object is detected or not, three possible actions, so to move the robot, to call a perception algorithm, to observe what's in front of the robot that has a camera on board, or to do nothing, to idle. There's a small cost for each moving and perception action, and there's a positive reward to achieve low uncertainty information about the position of the objects. First, I would like to show a video that illustrates the behavior of the architecture. So in the bottom left, you can see the global belief for each of the objects. And on the bottom right, you will see the image of the camera of the robot each time a perception algorithm is called. So first, we start with the uniform belief. And the system decides, has to decide where to explore first. So here, the goal is purely information gain, just get the positions of the three objects I mentioned before. So first, the video is accelerated. We don't have here, but it's every time the robot is moving is 30 times accelerated. Every time is looking into the object, 6 times accelerated. So first, the robot goes to the living room and goes between the locations, finds. OK. So it found the Coke, so the belief represents that. And it didn't find any other object, which also is representing the belief. So now the system decides to go to another region, goes to the kitchen, and it finds both objects that were missing. OK, so now another macro decision. Robot goes again to the living room because in the meanwhile, there was a decay on the belief of the Coke, and it already detected all the objects that it was looking for. So it goes again, checks the Coke is in the same place. Then same behavior, goes to the kitchen. Meanwhile, the Coke was changed from one place to another. Robot goes again to living room, and now guest found again in the new location, and the belief shows that. Now the Pringles also were here in the kitchen cabinet, now are on the bed. And we'll see again the belief representing the information about that. And the robot doing the execution goes to the living room, and now finally goes to the bed, finds the box of Pringles, and again keeps executing and keeps doing the execution. We change objects a few more times, and again we can see that it always updates the belief and gets the new information. OK, a few more on experiments, just to show some of the plots we have on the paper. So we plotted the information of the system in one experiment similar to this one, where we are changing objects and see the reaction of the robot. Our performance measure is the Ellinger distance between the current belief for each object and the perfect belief. When we mean perfect belief, is the belief that would be 0 everywhere, except for the actual state of the object. And we can see that the system tries to keep a low uncertainty information as possible, goes between different rooms, and tries to decrease the uncertainty. And every time the objects are changed from one location to another, it can recover from the lost information. Just another word on this last few time steps, that we really have a good information about what's going on in the environment. This is because all of the three objects were located in the same room, so it was much easier for the robot to get a good information on them. We also tested against incorrect observations. So what we did here was to compute policies with a given observation model. And then at execution time, we artificially introduced false observations to see what was the reaction of the system. And we can see that only after doubling the observations, predicting the observation model, we started to lose some performance. And now a different kind of experiment. We call it to carry out a task. So here we want to move one object close to the other without knowing their location a priori. So in this case, you can see that the robot explores the environment to find the information about the positions, finds the coke, grabs the coke, and explores the rest of the environment trying to find the box of Pringles. Once it finds it, releases the coke and finalizes the execution. For this experiment, we needed to change a bit the reward function, so we needed to add a reward for both objects to be located close to each other. And to conclude, in this paper we presented an integrated and efficient approach to represent the knowledge about an uncertain environment that is based on the hierarchical connection between probabilistic logic and decision theoretic planning. As a future work, we are thinking, among others, to include the cooperation between multiple robots to explore the environment, eventually to learn the model through interactions with the environment, and add the possibility to include or remove features from the model, for instance, to include new objects that were not predicted in the initial model, or new places that were also not included in the initial model. Well, that's all. Thank you, and open for questions.
So thanks. I like the hierarchical nature of the POMDP solving. I'm just curious, because you separate the information gathering and goal reaching into separate POMDPs. So one of the nice things in POMDPs usually is that you might actually find actions that it might not be optimal for goal reaching alone, and it might not be optimal for information gathering alone, but it actually is optimal in the sense that you can actually do this action and you can get both. So I wonder if you can still get this type of actions when you separate
so
in this way.
You mentioned this one, right?
Yeah, the separation of the...
Okay, the thing is, the goal here is exactly, well, I mentioned depends on the objective of the system. So if, like I was telling, if it's to carry a physical task, I need to define a goal. But if I just want to build the semantic map of the environment, then this is an information goal. That's why all the POMDPs are POMDPs with information rewards, because they are, the goal here is set on this side, not on this side.
Right. I guess what I'm trying to get at is that
maybe
for POMDPs, that is, there are actions that might be not optimal for goal reaching POMDPs, and also not optimal for reducing the uncertainty. Right. But that action is actually optimal if you combine both of them, because that same action can actually reduce uncertainty to some extent and progress to the goal. So I'm wondering if you separate the POMDP for information gathering and POMDP for goal reaching, like what you did, can you actually get that action?
That's all defined in the same POMDP.
Oh, is
because the POMDP allows to do that. We can define a belief-based reward, for instance, and the state-based reward to reach a particular goal. And then the POMDP tries to figure out, when it computes the policy, figures out what's the best way to get to his goals.
Sure.
Yeah. Maybe we're not being clear. We can talk. Yeah. Thank you.
I'm wondering how does your system represent multiple instances of the same object, like if you have two identical code cans?
Yeah, okay. So in this case, we need multiple. So we we need to know how many objects are for each one. So we need, if we have multiple cokes, we need to define coke 1, coke 2, coke, yeah, in this case, yes.
Okay. Questions? How do you want to deal with the learning? So there is this future work on learning.
That's a good question. Well, enforcement learning, probably exploring the environment and see. The thing is, we need to define by hand before or try to figure out the observation models. In this case, also transition models. We define by hand the possibility that a given object changes places. And that might depend on the environment, right? Mm-hmm. So even in different houses with different people, objects might change differently. So it would be nice to have some way to or to learn or to even update our model along the way. Mm-hmm. I think that would be the way.
Okay, so no initial idea about
not yet, yeah. It's like future. Okay. Actually, the thing we are working right now is actually in the last one, trying to add or remove features. Because I didn't mention, but the POMDPs we are using are solved offline, and we're trying to replace it with online POMDPs that allow this to be made easier.
Mm-hmm. Okay, thank you.
Thank you.
Okay, so we can thank the speaker and.